Hey everybody, let's talk about your rolling without slipping lab report. So here's a table of different moments of inertia, and let me just pick a few out. So let's say we go with the solid sphere, and that moment of inertia is 2/5 mr squared. And then let's go with the cylinder or disk. The moment of inertia is 1/2 mr squared. So notice that you can have a disk like this or a cylinder with the same mass and radius. The length doesn't matter. I mean, when you're rotating about this central axis, the length of the cylinder doesn't make a difference. Okay, and then how about this thin shell? So here the moment of inertia is 2/3. And then let's go with the hoop up here. Moment of inertia is just mr squared. Okay, so conceptually, the moment of inertia is larger when more of the mass is distributed farther away from the axis of rotation. So if you compare a hoop to a solid disk, so like let's say a hoop like this, rotating about its central axis compared to a solid disk, let's say that's like this. Right, so you see how for the hoop, more of its mass is distributed farther away from the axis of rotation, but for a disk, it's kind of evenly distributed. So then the hoop would have a larger moment of inertia. And then maybe let's see if you can convince yourself that if you have a cylinder, let's say you have a cylinder with some diameter d, and then I'll make this also diameter, the same as the diameter. So this is a cylinder, and let's say it's rotating about this axis. Now imagine you have a solid sphere with the same diameter d. See how it just kind of fits right in here? And if it's rotating about the same axis, do you see how the cylinder has like this extra bits in the corners? So the cylinder has more of its mass distributed away from the axis of rotation than a solid sphere. So we would expect a cylinder to have a larger moment of inertia than a solid sphere. Okay, now look at all this. What do they all have in common? They all look like, right, like some coefficient mr squared, like this. Some kind of coefficient. So for your experiment, the goal is find this. Find that coefficient. So you can kind of hypothesize if you rolled something that's more like a hoop, you're expecting a value that's kind of closer to 1. If you rolled something more like a solid sphere, you're expecting a value closer to 0.4. So really it's going to be some value between 0.4 and 1. And then the more of its mass distributed away from the center, the larger. Okay, now let's get to the actual setup. So if you had a ramp at some angle, you need to know that angle. And then whatever round object you sent rolling down the ramp, let's draw the free body diagram. Okay, so like this, all the forces acting on your round object. Let me try and get a nicer circle. There, okay. So the object has weight acting at the center of mass, so as weight, and then see how it's touching the ramp. So if the ramp is here, there's going to be some kind of normal force from the ramp, and then there's friction between your round object and the ramp over here. So there's going to be friction parallel to that ramp friction, and then this is going to be static friction if it's not slipping. Right, we're assuming it's rolling without slipping. So that would be static friction. And that's it. This is our free body diagram. Okay, so let's say if we pick coordinates like, I'm going to pick coordinates here like this. And I'm just picking it, I'm picking x this way because I know that the center of mass is going down the ramp. So I just said, let's make that positive. And then I only picked y here because if x is here and y is here, that means z is this way, out of the page. So then it's rolling in the positive z direction. It's rotating in the positive z direction. There's nothing wrong with rotating in the negative direction, but I just wanted to have positive values. Okay, and then the angle here has got to be right here. Okay, so now let's practice writing Newton's second law for rotation. So that's some torque about wherever you want. So I'll choose the center of mass. So I'm summing the torque about the center of mass. So about over here, this force doesn't cause any torque, right? Because it's going right through that point. This force also does not provide any torque about this point because it's just going right through it. Only this force. Okay, so then the lever arm from here to here is R times this, and it's going to go this way, which is in the positive z direction. So this is positive. Okay, so there's only the one torque equals I alpha, so that's the moment of inertia. But which moment of inertia? Because I sum torque about the center of mass, this moment of inertia should also be about the center of mass. Okay, let's see. I don't know this, so we need more equations. So let's sum forces in the x direction, sum forces in the y direction. Okay, so in the x direction, I chose x over here, so we got the x component of that, mg sine theta, that's in negative, equals mass times acceleration, and that would be the acceleration of this point, the center of mass. Okay, y direction, y is over here, so mg cosine theta minus n equals mass times acceleration of the center of mass, which is this. And I know the center of mass is only accelerating this way. There's no motion this way in the y direction. So ay is 0. Okay, and then last thing, if it's rolling without slipping, it's a special case situation where the acceleration of the center of mass equals r alpha, the radius and the angular acceleration. And we just said that this is the acceleration of the center of mass. So for this example, ax, which is the acceleration of the center of mass, is r alpha because it's not slipping. Because it's not slipping, we can write this. Okay, so let's solve for, let's say, the acceleration. So I can combine this, and see acceleration right here, this. I'll combine these three. Let me label these. Okay, so from, let's say, which is easiest, I'll combine this and this, so 1 and 4. RFS equals I alpha, but alpha is AX over R. Okay, and then let me just move this R right over here. There. Now I can substitute this right here into equation 2. So mg sine theta minus fs, which is right here, equals max. Okay, so then I can solve for ax. Let me just move this on this side of the equation. Okay, and how about I see the mass over here? I'll divide everything by mass. Since mass is non-zero, you can divide by something that's non-zero. Okay, so then that, let me simplify this a little bit. There. Okay, and then I'll just move this in the denominator. Okay, so here's the acceleration. And notice, see here, this is the moment of inertia. See how we just talked about this over here? Where the moment of inertia is some kind of coefficient times mr squared. Why don't I put that over here? Moment of inertia is some kind of coefficient times mr squared. And now see how that just cancels? So then we could write it more like this. There. For this x being that coefficient. Right, so like a hoop will be 1, a solid sphere would be 2/5, and then whatever you have will be in between those two extremes. Okay, but that's not something we have, right? You know g, you can measure the angle, but how are we going to get the acceleration? So let's get this so that we can measure some data. So if you roll down the ramp and you measure the distance, right? So if you're here and you measure this distance and the time, and those are known, and you know the angle. Notice how this acceleration is constant, which means we can use kinematics for constant acceleration, like this, and this one. Okay, so, and then we just look at it like, which would be useful to us? We measure the distance, we measure the time, which means we would know this and time, and then we got the expression for acceleration right here. So I think we should use this. Okay, so let's use this. Never mind, I'm just going to erase this. Okay, so x minus x naught is that distance d that you measured right here. And then v naught, initial velocity, if you start at rest, that's 0. And then we're just left with 1/2 ax t squared. T squared. Okay, and then let's solve for this coefficient. Okay, so I can maybe leave you to do that. Or here, right, just move this over here. Let's just exchange these two. So then g sine theta, Then there's t squared in the numerator. There's the 2 in the denominator, and d over here. And then just see this 1, just minus 1 over here. And there you go. Okay, so this is that coefficient for whatever shape you were rolling down your ramp. Okay, so just for practice, because I mean you still need to know this stuff for the lecture component of the class. You see how here I sum the torque about the center of mass? Let's try summing the torque about somewhere else. Okay, so I'm just gonna reuse that same free body diagram. Okay, so instead, let me see if I can just move my coordinate here. Yep, can. Okay, how about I pick my coordinate here, the origin here, where the round object is in contact with the ramp over here. So let's sum torque about my new origin. I'll just say over origin over here. Okay, so the torque about here from due to normal force N, 0. The torque here due to this friction force is 0. There would only be torque from the weight. Okay, so there's this point here, and then this force here. Only the perpendicular component of the force really provides any torque, right? So like we're talking about here, the weight is like this. If you decompose this force into components like this, then this component in this direction would be mg cosine theta. This component would be mg sine theta. And then if you did this cross product, like R cross F, see how these are parallel? So this force doesn't provide any torque. Only this one. Okay, so I'm gonna write the torque would be R times mg sine theta. And that will cause a torque this way, which is in the positive z direction. So this is positive. And then that's it. That's the only one torque. Equals I alpha. But last time we summed the torque about the center of mass here. And so then the moment of inertia was about the center of mass here. This time we sum torque about here. That's not the center, right? So this is the moment of inertia about, right, here, not here at the center of mass. So which is more? About the center of mass is always a minimum, right? So the moment of inertia about that origin is definitely more. It's the moment of inertia about the center of mass plus extra. Okay, how much extra? The mass of the object times the distance between these two parallel axes squared. So for this example, the distance between the two is the radius r. So that squared. Okay, so this is the moment of inertia that goes here. And then if it's rolling without slipping, then the acceleration of the center of mass is r alpha. Okay, so let's combine all of this. So let's see. I'll put this here, and then I'll put this here. So let me do that. So r mg sine theta equals I about that origin, which is center mass plus mr squared. And then alpha is a over r. Okay, now let's solve for the acceleration of the center of mass. So let's see, how can we clean this up? See this mr, I'll just move it over here. Okay, and then I'll just multiply this through over here instead. There. Okay, and then here, let me just rewrite it. Okay, and then this can go in the denominator. And then again, the moment of inertia is some kind of coefficient, mr squared, right? So I replace that with whatever coefficient, mr squared, and then you see how this cancels. So then it just looks like this. Okay, so there's the acceleration of the center of mass. When we sum the torque about over here, right? As opposed to the last time when we summed the torque about the center of mass. And then we got this answer. This time we have the exact same answer, which it should be, right? It's the same exact part. Okay, so for your lab report, the introduction, you can explain this part where the moment of inertia, right, depends on how the mass is distributed closer to the axis of rotation or farther away from the axis of rotation. And then there's just this coefficient that differs depending on the shape. And then you can go over this derivation and then solve for the acceleration, and then using kinematics for constant acceleration, you can get an expression for that coefficient, this one. And then you can, right, and then you have that's your introduction. Then you have your methods. You just describe in enough detail what you did so that someone else could read it and follow, copy your methods. Then the results. And then here you can show a picture of your setup in your lab report as well. And then analysis. Here you can compare what you calculated here, what you would expect to get based on the shape, and then compare it to what you actually measured. And then also sources of error, like what sources of error. And then conclusion. In the conclusion, you can basically just restate your hypothesis that you would have in the intro and hypothesis. So you could say, for example, I think the hoop is going to have a larger moment of inertia than the disk, which is going to have a larger moment of inertia than a ball. So then that's your hypothesis. And your conclusion, you kind of just restate that and then say the results. And then whatever references you had. Okay, so let me know if you have questions. You can just post it to the forum. Other than that, I'll see you in the next video.